Hi, my name is Jamil, and today in this section we'll be looking at exponential and logarithmic functions and some of their applications. Our objectives will be the following: to look at physical science applications, financial applications, and biological and medical applications. Exponential functions are used in many different settings. We're going to take a look now at some exponential decay and exponential growth functions. Here we're given the exponential growth function. A of t equals a sub 0 e raised to the kt. In this function, a sub 0 represents the initial quantity present, t is the amount of time elapsed, k is greater than 0, and that represents the growth constant, and a of t represents the amount present at any time. Similarly, we have the exponential decay function. Here we see the exponential decay function, which is given by a of t equals a sub 0 times e raised to the negative kt, where again a sub 0 represents the initial quantity present, t is the time elapsed, k greater than 0 represents the decay constant in this case, and a of t represents the amount present at time t. Now, one application of exponential functions is used with radioactive decay. To use radioactive decay, we first need to understand what a half-life is. A half-life is the amount of time that it takes for half of a substance to decay. Let's take a look at this problem. The half-life of radioactive lead-210 is 21.7 years. Find an exponential decay model for lead-210. Using the exponential decay function that we just saw, a of t equals a sub 0 e raised to negative kt, and keeping in mind that the half-life for this particular element is 21.7 years, we should be able to complete the function. So what we need to do is keep in mind that we're dealing with a half-life, so the amount present is going to be equal to 1/2 the amount that we started. So the initial amount, to make it easy in this case, we'll choose as 2. So we're going to let a sub 0 equal 2. And that means the present amount now would be 1 because we're a half-life later. And then filling in the rest, we have e raised to the negative k times the time for a half-life, which is 21.7 years. Now, working this out, we're going to solve this equation for k. So we'll start by dividing both sides by 2, which will give us 1/2 equals e to the negative, and we're going to end up with 21.7k in the exponent. Now, taking the natural log of both sides to get rid of the e, we end up with the natural log of 1/2 equals negative 21.7 times k. And then multiplying both sides by 1 over negative 21.7 to isolate k, we have 1 over negative 21.7 times the natural log of 1/2 equal to k. And that's the exact value of k. But if we were to put this into a calculator, the calculator would round this value to be 0.032. So now let's go ahead and look at the second part of the question. Here we're asked, how long will it take a sample of 500 grams to decay to 400 grams? So again, what we're going to do is we're going to use the exponential decay model. So we start with 500 grams and we want to decay to 400 grams. So a of t would equal 400. The initial amount would be 500. And we've got e raised to the negative 0.032, because that's the decay constant we found from the last part of the example, times the time. Now, to find out how long this would take, we need to solve this equation for t. So dividing both sides by 500, 400 divided by 500 gives us 4/5, and that equals e raised to the negative 0.032 times t. Taking the natural log of both sides, we end up with the natural log of 4/5 equals negative 0.032 times t. And then finally, multiplying both sides by 1 over negative 0.032, we get that times the natural log of 4/5 equals t. So again, if we were to use our calculator, we'd find that the approximate value for time here would be 6.973, or in other words, it would take 6.973 years for the substance to decay from 500 to 400 grams. Let's now look at the third part of this example. How much of the sample of 500 grams will remain after 10 years? Well, again, we're going to go back to our decay model. So we have a of t equals a sub 0 e to the negative 0.032t. And in this example, we're told that we start with 500 grams and asked to find out how much is left after 10 years. So we know that a sub 0 is 500 grams. So we're really asked to find out what a of 10 would be. In other words, when time is 10 years. Given that a sub 0 is 500, and we know, of course, that e raised to the negative 0.032, and then t is going to be 10. So working this out, we find that that equals 500 times e to the negative, and multiplying the 0.032 times 10 gives us 0.32, and then working that out on a calculator, we find out that the answer is 363.075 grams. So that's the amount of the substance that would remain after 10 years. Another use of exponential functions revolves around finding the age of a fossil. This is called using carbon dating. Let's take a look at an example that does this. Carbon-14 is a radioactive form of carbon that is found in all living plants and animals. After a plant or animal dies, the radiocarbon disintegrates. Using a technique called carbon dating, scientists determine the age of the remains by comparing the amount of carbon-14 present with the amount found in living plants and animals. The amount of carbon-14 present after t years is given by the exponential function defined by a of t equals a sub 0 e to the negative kt, where k is equal to the natural log of 2 times 1 over 5700. We're asked here to find the half-life. So, in order to do that, what we're going to do is start with our decay model. The a of t equals a sub 0 e raised to the negative natural log of 2 times 1 over 5700 times the time. And since we're dealing with a half-life, what we need to do is start with an initial amount that's twice what we have presently. So again, what I'll do is make a sub 0 equal to 2, and a of t equal to 1, and fill in the rest of the function, which is e raised to the negative ln of 2 times 1 over 5700 times t. And now dividing both sides by 2, we end up with 1/2 equals e raised to the negative ln of 2 times 1 over 5700 times t. Now taking the natural log of both sides, we end up with the natural log of 1/2 equals the negative natural log of 2 times 1 over 5700 times t. And now from here what we're going to do is we're going to divide both sides by negative ln of 2 and multiply both sides by 5700 at the same time. And what that will result in is 5700 on the top, negative natural log of 2 on the bottom, times the natural log of 1/2, and that equals t. And now making use of some logarithm rules, we can use the natural log of a over b equals the natural log of a minus the natural log of b for the ln of 1/2. So what that gives us is 5700 over the negative ln of 2 times, now making use of that rule, the natural log of 1 minus the natural log of 2 equals t. And now you may know that the natural log of 1 is equal to 0, so that's just going to be 0 there. And now we have a negative natural log of 2 factor here with a negative natural log of 2 factor in the denominator, so those will cross out, and that leaves us with t equals 5700 years. And that is the half-life for this particular substance. Another application of using exponential growth and decay functions is in the world of finance. Let's take a look at an example where we're going to amortize a loan. The amortization payments. A loan of P dollars at interest I per period may be amortized in n equal periodic payments of R dollars made at the end of each period, where the payment amount R is equal to P divided by the quantity of 1 minus the quantity 1 plus I, all raised to the negative n, all divided by I. And the total interest I that will be paid during the term of this loan is given by I equals n times R minus P. Let's take a look at an example that involves this. Following the traditional American process of haggling, you agree to purchase a used SUV for $24,000. After a down payment of $4,000, the balance will be paid off in 36 equal monthly payments at 8.5% interest per year. Here you're asked to find the amount of each payment and how much interest will you pay over the life of the loan. So in order to do this, we need to take a look at our formula and figure out what each unknown stands for. So R is the payment amount, and that's what we're looking for. So we need to figure out what our value of P is. Now remember, this vehicle cost $24,000, but we started off by making a down payment of $4,000, so we can subtract $4,000 off of it right away. That means we're going to need to make a loan of $20,000. So our value for P is 20,000. Now the next thing we need to find out is what our value of I is. Now I is the interest rate, and our interest rate we were given was 8.5%, but since this is being compounded monthly, we need to divide that by 12. So I has the value of 0.085 divided by 12, which is equal to approximately 0.007. I'm sorry, 0.007083. Now, the last thing we need is to know the value of n, and in this case, since we're paying it off in 36 months, the value of n will be equal to 36. So using these values in our formula, what we find is R equals, and it's going to be 20,000 all over 1 minus 1 plus our value of I, 0.007083. All of that raised to the negative n, which in this case is negative 36, and then divide that all by our value of I, which we found to be 0.007083. After working this out, we find that our monthly payments turn out to be $631.35. Now, the next question was to find the total amount of interest paid over the life of this loan. So here we're going to use our formula I equals n times R minus P. Our interest amount is what we're looking for. N is the number of payments, so that was 36. R stands for the amount of each payment, which was $631.35, minus P, which as you may remember was 20,000. After working this out, we find that the total amount of interest we pay is $2,728.60. Now you've seen one of these problems done, why don't you take a minute and try this next one on your own. Here you're told that $8,500 is amortized over 4 years with an interest rate of 7.5%. You're asked first to find the monthly payment, and then find the total interest that will be paid during the loan. Give this a try and then check back with me when you've completed it. Okay, let's see how you've done with this. You were given that $8,500 was to be amortized over 4 years with an interest rate of 7.5%. So to do this, we need to take out our formula and figure out what all the unknowns are. So here, we're looking for the payment per month, which is R, so that's what we're trying to find. We're told that the p-value is $8,500, that our interest rate was 7.5%, and once again we have to divide that by 12, so that's 0.075 divided by 12, which gives us an approximation of 0.00625. And then n, or the number of months that we were doing it, is equal to 48. So using these values in our formula, we find that the monthly payment R is equal to 8,500, all divided by 1 minus 1 plus 0.00625, raised to the negative n, which is negative 48, then all of that over I, and we found our I value to be 0.00625. So using a calculator and computing that answer, we find that our monthly payments turn out to be $205.52. So now, once again, they've asked us to find the total interest paid. So using the formula for total interest, interest equals n times R minus P. What we find out is that our n value of 48 times our monthly payment value of $205.52 minus the 8,500. When we work that out, what we see is that the interest, or the total interest paid, is $1,364.99. One last place we'll look at applications for exponential functions is in population growth. Let's take a look at this last example. Escherichia coli is a strain of bacteria that occurs naturally in many organisms. Under certain conditions, the number of bacteria present in a colony is approximated by the following function. A of t equals a sub 0 e raised to the 0.023 t, where t is measured in minutes. If a sub 0 equals 2.4 million, then find the number of bacteria at each time. The first example, 5 minutes. Second example, 10 minutes. Third example, 60 minutes. So we'll get our exponential growth function out. And using that, we know that a of t, in the first example, we're looking for time when time is 5, so that's really a of 5. And that's going to be equal to 2.4 million times e raised to the 0.023, and the t value again is 5. So, using the calculator and working that out, what we find out is that a of 5 is equal to 2,692,800. So that would be the population after the first 5 minutes. In the second example, we're asked to do the same thing, but this time find the population after 10 minutes. So finding a of 10 means substituting in t equals 10 into our function, and then using the calculator to compute this, we find that after 10 minutes, the population is 3,021,600. So that would be how many bacteria are present after 10 minutes. Then the last example, we're asked to find the amount of bacteria present after 60 minutes, or 1 hour. So that would be a of 60, since t is being measured in minutes. And that's 2,400,000 e raised to the 0.023 times 60. And using a calculator to assist us, we can find that the number of bacteria present after 1 hour, or after 60 minutes, is 9,540,000. In this section, you've seen many different applications and uses for exponential and logarithmic functions. You should continue to practice these examples by doing the exercises in your textbook. Have fun, and I'll see you next time.